An alternating series is any series where consecutive terms, well, alternate in sign. Generally, it has to be some pattern that they alternate in, but for most of the ones that we're going to see, it's actually going to go like plus, minus, plus, minus, plus, minus. Now, the things that generally make a series alternating are terms like this, like a -1 to the n. Another way that we can write it, kind of weird, is cosine of n pi, right? Because that'd be cosine, if n goes from 1, it's cosine of pi, which is -1, 2 pi, which would be 1, 3 pi, -1. Another kind of special way we can do it was with the sine function. Now this one can be kind of messy. This is 2n, well, plus or minus 1 pi over 2. So think about this as really just the odd multiples of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. So all three of these are all alternating. Now, of course, the one that we're going to see the most is -1 to the n, but it can be replaced with either one of those. So if you see these, it's the exact same thing as our -1. All right, so what does an alternating series test say? Well, it says if we're given the series, the sum n equals, let's go from 1 to infinity, -1 to the n, a sub n. Now this is a little bit different from any other series that we've defined. We've generally defined everything inside the summation as a sub n. This is where this one gets a little bit confusing. Now our a sub n is everything except for the alternating part. So basically we're pulling that alternating part out and we're going to ignore it. If we're given this series, and let's say the limit as n goes to infinity of a sub n is equal to 0, and a sub n plus 1 is less than or equal to a sub n for all n, then we can say this. Then the sum n equals 1 to infinity, -1 to the n, a sub n converges. All right, now notice that this test says nothing about divergence. You're never going to say that something converges by the alternating series test. Generally, if it fails one of these two, and it's generally going to be this one that it fails, that means it would fail the nth term test immediately anyway. And so we always kind of watch out for that. So our alternating series test only tells us about convergence, never tells us about divergence. Well, now that we've introduced this alternating part, we've actually introduced another type of convergence that can happen, and this is called absolute and conditional convergence. All right, now again, my notation is going to be a little bit weird here. You're going to kind of see this in almost every textbook that you read, and I'm sorry for the confusion here, but you'll see what I mean. If this is true, if the sum n equals 1 to infinity, if this is what we're looking at, we're given this. If the sum n equals 1 to infinity, the absolute value of a sub n converges, we say it converges absolutely. So now notice the difference here, and this is where I'm saying about the small difference. Here, a sub n is everything inside the summation. When we're talking about an alternating series, the a sub n is everything except for the alternating part. Basically here, kind of get the idea. When we slap absolute values on this, that means that every term is going to be positive, which means the alternating piece goes away anyway. So if we say that that's true, that the absolute value of the series converges, we say it converges absolutely. Now, kind of the good news here is this is something you can do immediately by looking at your series. Most of the series that we've dealt with so far, every single term is already positive, which means we're already found out that it was actually absolutely convergent. Now, here's where it gets a little bit tricky. If the sum n equals 1 to infinity of a sub n converges, but the sum n equals 1 to infinity, the absolute value of a sub n diverges, it is said to be conditionally convergent. All right, now the good news here, this is generally talking about alternating series. That's why it's in the alternating series thing. So here's the idea. The original series, whatever it is, converges, but then we turn around and make every term positive. Basically, it doesn't go positive, negative anymore. If that diverges, we say converges conditionally or is conditionally convergent. All right, let's just try a few examples here of how to use our alternating series test and whether or not to determine things are absolutely or conditionally convergent. So let's start with determine if it converges. I need all the letters in there. Or diverges. If it converges, state if it is absolute or conditional. Okay, so here's the kind of thing. Anytime you're dealing with alternating series, you're definitely going to want to look for either absolute or conditional convergence. Let's get our test out of here and just try a few of these. Now, we're going to go through this kind of two ways. The first time I'm going to do this, I'm just going to be demonstrating the exact alternating series test, but then we're going to take a look at absolute and conditional convergence. So first off, we're just told to check the alternating series test. So the first thing we want to do is figure out what A sub n is. A sub n, when we're talking about the alternating series test, is everything except for the alternating part. So this is 1 over n squared. All right, we have two tests to do here. We want to do the limit as n goes to infinity of A sub n. That is 0. That's pretty obvious. And we have to also show that A sub n plus 1 is less than or equal to A sub n. Well, A sub n plus 1 is going to be 1 over n plus 1 squared. Less than or equal to A sub n is 1 over n squared. Right, A sub n plus 1, think about it as kind of like functional notation. Everywhere there's an n, we put an n plus 1. Now, we need to say whether or not this is true or false. If we cross multiply, n squared is less than or equal to n plus 1 squared. We could do some more algebra there, but I think it's pretty obvious that that would have to be true. So I'm just going to say that that's also true. So this converges by, now you're going to see this a lot, abbreviation, alternating series test. All right, so, but that doesn't talk anything about being conditionally or absolutely convergent. That's how the alternating series test works. Now, what I would suggest is anytime you see an alternating series, always do this first. For always check for absolute convergence first, because if it's absolutely convergent, that's actually more convergent than conditionally convergent. If it's conditionally convergent, kind of means, well, it'll converge, but only under certain conditions kind of idea. So what we should have done is let's take our A sub n here. Now again, A sub n here is going to be different over here because we're checking for absolute convergence, would be negative 1 to the n over n squared. So you can see how this would be a little bit confusing. So the absolute value of A sub n, the absolute value negative 1 to the n over n squared, would just be 1 over n squared. Right, because the top's either positive 1 or negative 1, and the absolute value of both of those is a 1. So now we just want to look at the sum n equals 1 to infinity 1 over n squared. Well, this is a convergent P series. Here we got P is equal to, which is greater than 1. So since this converges, that means our original thing actually converges absolutely. So the sum n equals 1 to infinity, negative 1 to the n over n squared converges, which we already decided that it converged, right? But over here we can be more specific and say it converges absolutely. So notice here that checking for absolute convergence actually negates some of this work, right? We didn't have to do this if we would have checked for absolute convergence first on this problem. So let's try another example and see why you're always going to want to check for it first and how it doesn't always work. Let's do almost the exact same problem. Watch, I'm going to change this one thing there. Notice all I did with our last series, I went from n squared and I changed it to n. Now a lot of our work here is going to be pretty close to what we just did. So we should be able to recognize that this is an alternating series. So since it's an alternating series, we want to check absolute convergence first. So when we're checking for absolute convergence, our a sub n is everything up there over n. So the absolute value of a sub n is going to be -1 to the n over n, which is just 1 over n. So we want to look at the sum n equals 1 to infinity of 1 over n. Well, this is a divergent p series. Here we have p is equal to 1. Okay, so this is not absolute convergence, which means that it may converge, but it may need the +1, -1, +1, -1 to help it converge. So since this didn't converge, let's actually look at now we're going to look at conditional convergence. So basically, we're back to where we started the original problem, and I want to look at, does this converge? So sum n equals 1 to infinity, -1 to the n over n. So you say, well, this is a alternating series, so let's try our alternating series test. For our alternating series test, my a sub n is just 1 over n, right? We ignore the alternating part when we define our a sub n. We need to check two things. The limit as n goes to infinity of 1 over n, that is 0. And I need to show that a sub n plus 1 is less than or equal to a sub n. So 1 over n plus 1 is less than or equal to 1 over n. Cross multiply, everything's positive, so we don't have to worry about it. N is less than n plus 1. Okay, so we can now say this converges by our alternating series test. Okay, now what else can we say? Not only is it convergent by our alternating series test, since it's not absolutely convergent, this is conditionally convergent. Okay, now here's why you always want to do absolute convergence first. You check this real quick. If it converges, you say it converges absolutely, and you're done. If it diverges, then you do have to switch over and do your alternating series test, and you say, okay, if it converges or diverges here. Now, if it diverged here, so it would be divergent here, so it's always divergent. If it's divergent here, but converges here, that means it does converge, but it converges conditionally, only when we have the alternating piece. All right, let's maybe do one more here. Let's make it a little bit more messy, at least algebraically, since we had two pretty easy ones there. What if I had something like the sum n equals 1 to infinity, let's do cosine n pi, let's go 2 to the n over n factorial. Okay, so first off, the hard thing here is recognizing that this is an alternating series, right? The cosine n pi is really kind of the same thing. The cosine of n pi is really the same thing as our -1 to the n. So this is really just an alternating series. So we're going to check for absolute convergence first. So my a sub n is everything here. cosine n pi to the n over n factorial. So the absolute value of that, cosine n pi to the n factorial. Well, since cosine is either positive or negative 1, when we do the absolute value of that, it just makes it positive. So there's what we actually want to take a look at. So what's the sum n equals 1 to infinity of 2 to the n over n factorial. All right, I'm back. So the confusion, what you were doing here, we can't do this yet. I forgot we haven't done our ratio test yet. Our ratio test is coming up probably in our next video. So I'll tell you what, we're gonna stop right here. We'll finish this up in the next video on how to do this. But remember, for our alternating series test, we do always want to check for absolute convergence. By the way, I'm gonna give you kind of a spoiler here. This actually converges. This converges, so that means that the sum n equals 1 to infinity cosine n pi 2 to the n over n factorial converges absolutely. All right, yeah, I forgot that we did our test a little bit out of order here. So we haven't actually seen this video yet. So in the next video, when we take a look at our ratio test, I'll prove to you that this actually converges, and which means our original series converges absolutely. Now, since it converged absolutely, we do not need to check to see that it converges conditionally, right? Absolutely is more powerful than the conditional convergence. So for your alternating series test, if you are doing the alternating series test, you need to define a sub n as everything but the alternating part. The limit as n goes to infinity of a sub n has to be less than 0, and a sub n plus 1 is less than or equal to a sub n. If that's true, you say it converges by the alternating series test. You never say that something diverges by the alternating series test.